Bismillahirrahmanirrahim. How are you, students? Today we will start a new chapter, fluid dynamics. We already started. Sorry. In this chapter, this is lecture number 26, class first year. Now, students, today we will study Bernoulli equation. So first we will go into detail of Bernoulli equation. The statement written here is difficult to understand. I will try to make it easier for you people. Bernoulli equation is an equation which if you take a system like this, if you take a system of pipe in which water is flowing here, if you look this one, it seems awkward, but try to understand. Here the area is less and here is the area is greater. So where area is greater, pressure will be less. Pressure will be less. Where area A1 is less than area A2, then velocity V1 will be greater than A2. Then velocity 2. Where velocity is greater, area will be less. Where area is greater, velocity will be less. So Bernoulli equation states that within a horizontal flow of fluid, points of higher fluid speed will have less pressure than point of slower fluid speed. Where velocity is more, pressure will be less. Velocity is velocity is greater. There pressure will be less, area will be less. This is Bernoulli equation. Bernoulli principle. At a point of horizontal streamline, higher pressure region have lower fluid speed and lower pressure region have higher speed. The relation between the pressure, flow speed and height per flow of an ideal fluid is called Bernoulli equation. Bernoulli equation states that the sum of all form of energy in a fluid flowing along an enclosed path is the same at any 2 points in that path. For example, water is flowing in this direction. Here area is greater, A1. Here area is A2. A1 is greater. A1 is greater. A1 is greater than A2. So here velocity will be lesser. Area is greater, velocity will be less than V2. Here velocity will be greater and velocity will be less, pressure will be less, area is greater. Flow is steady, streamline flow. For Bernoulli equation, the condition is the flow must be streamlined. Density will remain constant. The fluid must be incompressible. Friction will be negligible. There will be no friction. The density will remain constant. The fluid is incompressible. Fluid is steady. Remember these conditions. Now you will do it by yourself. You will do this theory by yourself. I will explain. Pressure, potential energy, kinetic energy at one end will be equal to the pressure, potential energy and kinetic energy at the other end. Now remember that here kinetic energy will be equal to V1 is equal to half mv1 square. At this end, potential energy will be equal to mgh1 and pressure will be P1. For the other side, I will write on the next page. Now I will do the derivation here. At one end pressure is P1, kinetic energy is KE1, and potential energy is mgh1. Potential energy is 1. We will write the relation for this one. Now at the other end pressure will be P2, kinetic energy will be KE2, and potential energy will be PE2. So pressure P1 plus kinetic energy at that end plus potential energy at that end will be equal to pressure P2 plus kinetic energy 2 plus potential energy 2. All these will be equal. All these will be equal. Now I will calculate work done. Work done is equal to force into displacement. Force into displacement. Here the displacement is del x1. Here the displacement is del x2. Here pressure is P1, area is A1, and force is equal to pressure into area. This is a point del N1 W1. W1 is equal to P1 A1 del x1. D1 is equal to del x1. Pressure is equal to force per unit area. From this, force will be equal to pressure into area. So W1 is equal to P1 A1 del x1. S1 is equal to V1t. Del x1 will be equal to distance, will be equal to velocity 1 and right t. Time will remain same. So W1 is equal to P1 A1 V1 t, velocity and t. This is the equation for W1. P1 A1 V1 t. Now similarly this equation can be written for del V also, for the second side. W2 is equal to similarly P2 A2 V2 del t. T is equal to del t. Now write it in calculated form. W is equal to W1 minus W2. P1 A1 V1 del t minus P2 A2 V2 del t. Now according to equation of continuity, A1 V1 is equal to A2 V2 is equal to rate of flow of volume. Rate of flow of volume. I will write the simple value for this one. Volume flow rate. Volume flow rate. This is equal to AV. So I will write, erase again. Remember this equation. A, V and del T you will write. It is equal to, del T is equal to volume del V. So A V is equal to del V divided by del T. This is the statement of equation of continuity. So W will be equal to P1 minus P2. Area is common, V is common, and del T is common. But in place of this we will write volume. P1 minus P2 and del V volume. Density is equal to mass per unit volume. So volume will be equal to mass per unit density. So in place of del V you will write mass per unit volume. W is equal to P1 minus P2 mass per unit density, equation A. Similarly, work done will be equal to change in kinetic energy plus change in potential energy. I will erase, you keep on writing. Work done is equal to potential energy 2 minus potential energy 1 plus kinetic energy 2 minus kinetic energy 1. So W will be equal to mg h2 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 minus mg h1 plus half mv1 v2 square minus 1 divided by 2 mv1 square. Compare this equation with the previous equation. P1 minus P2 is equal to mass per unit rho is equal to mgh2 minus mgh1 plus half mv1 v2 square minus half mv1 square. Now take this to other sides. Now arrange P1 plus 1 divided by 2 mv1 square P1 minus P2 mass per unit density mgh1 h2 minus mgh1 plus half mv2 square minus half mv1 square. Mass cancel and density will be multiplied. So equation in simple form can be written as P1 minus P2 is equal to 1 divided by 2 rho v2 square minus 1 divided by 2 rho v1 square plus rho gh2 minus rho gh1. P1 plus 1 divided by 2 rho v1 square plus rho gh1 is equal to P2 plus 1 divided by 2 rho v2 square plus rho gh1. This equation is applicable when there is no frictional forces. So it is the manifestation of law of conservation of energy. This is very important. So do revise. Now we will go into detail of filter pumps, vacuum pump, and like we do these things. First is application of Bernoulli equation. This is the first application, this one, vacuum pump. So jet and nozzle is the other application. Simple. Keep your approach simple. Where pressure is high, speed will be low. Where pressure is high, speed will be low. But let's say we have two common areas. Ignore the practical example. Here pressure is high. P2 is greater than P1. P2 is greater than P1. So Here the area will be greater and velocity will be less. Here area will be less, velocity will be greater. If pressure is greater, P1 is less than P2, area 1 is less than area 2, then V will be greater than V2. Where pressure is low, area is low, velocity will be less. Where pressure is less, area is less, their velocity will be greater. I will take a simple example. Vacuum pump used to assist laboratory filtrations in which a jet of water inside a glass tube entrain air molecules from the system to be evacuated. So take a simple example. This is a utensils containing water. Here here green line, here area is less. Now look students, air will enter here. Here pressure is P1, area is A1, velocity will be V1 at this end. Now take the other end, this end. Here pressure will be high and area is greater. So velocity will be low. Here the area of atomizer decreases. So pressure will be low. This pressure will be greater than this one, and this area is greater. Here velocity is V2, so V2 will be greater than V1. So where area is less, area will be greater. Now here water is entering because here atmospheric pressure is exerted here in this area and in this area. It pushed the water. I will draw again. This is a container containing water. I will draw it like this. I will draw again. Now here is water. Here is a gap, hole. Here there is this. Here is a gap. Air can enter here. Atmospheric pressure also act here. Here air is entering, but at this point pressure is P1, velocity is 1, area is A1. Here area is greater, pressure is greater. Here pressure is less, area is lesser. But here the velocity will be lesser, and here at the other end velocity will be greater. So where area is less, velocity is greater. Pressure is less, area is lesser. So simply you can say that where speed is high, pressure will be low. Where speed is high, pressure will be low. So I will explain. I will take an interesting example. Now here an object is moving here. An object is moving with high velocity. You are standing at this location. You are standing here. Now here it is moving very fast. So the airspeed between this object and your position will be high. Velocity will be v1, and here the velocity will high. Here the speed of velocity will be low. So v2 will be less than v1. I will draw again. Here an object is moving. You are standing at this location. Here speed of air is v1, and here the speed of air is v2. So it is moving very fast. So in this area velocity will be high as compared with this area. So v1 is greater than v2. So I will use red. Here the speed is high, so pressure is p1, and here pressure is p2. So here speed is high, pressure will be low. So here pressure is p1, which is less than p2. Here the pressure will be high. So when a fast moving train is moving near you, fast moving train is going in this direction, and you are standing at this position exactly. Here pressure will be low, so and here the pressure is p2 will be greater. So if a fast moving car is moving near to you, so the pressure on you increases, which push you towards the car. You are falling towards the car. Now students, take a bottle of perfume. Here the opening is narrower. Here air is coming. So velocity will be low, pressure will be high, area is greater. Here area is less, pressure is less because area is less. So here velocity is v2. Here velocity will be greater than v1. So air coming here will push the perfume. Atmospheric pressure is exerted on the perfume in the fluid, which pushes it in the upward direction, and here it will come. Where area is here, the area is less. So when high pressure is exerted on a very small area on a fluid, it will convert fluid into small droplets. Into small droplets. So simply you can say that where pressure is high, velocity will be low. Where velocity is high, pressure will be low. Where area is greater, velocity will be less. Where area is less, pressure will be high. Thank you, students. In the next coming lecture, we will do the Torricelli theorems and Venturi relation and some other topics. Practical application of Bernoulli equation we will do. Thank you, students. Wish you best of luck. Allah Hafiz.